In this video, I'm going to show you how to find the antiderivative. Sometimes people call it the indefinite integral. Now the antiderivative is represented by capital f of x, whose derivative is f of x. Now the process of finding antiderivatives is called antidifferentiation, or sometimes integration. To find an antiderivative, we go backwards to find the original function. Now before we do that, let's take a look at these examples here and let's find y prime, or the first derivative. So y equals x squared plus 5, y prime is equal to 2x. The second one, y equals x squared minus 3, y prime equals 2x again. The last one, we have y equals x squared plus 10.3, and y prime equals 2x again. So you will notice that y prime is equal to 2x for all of the questions. However, if I give you y prime equals 2x, I could say that y is equal to x squared plus any different value of numbers. We can have 5, negative 3, it could be anything. So what we use is the letter c to represent this constant. And we call it an arbitrary constant because it can be anything. So in function notation, we have f prime of x equals 2x, then capital F of x is equal to x squared plus c. So the theorem states that if capital F is the antiderivative of lowercase f on an interval I, then the most general antiderivative of f on that interval is f of x plus c, where c is an arbitrary constant. So let's take a look at these examples. Now, before I do them, I want you to actually pause the video and see if you can actually figure them out for yourselves, just from using logic and what you've done already with derivatives. So pause the video now. All right. If you gave it some thought, you will find that the first one, capital F of x is equal to 7x plus c, because if I take the derivative of 7x, I will just get 7. The second one, capital F of x is equal to x squared divided by 2 plus c. So when I take the derivative of this function, I'm going to bring the 2 down to the front. So I have 2x, and it'll be to the power of 1, but then the 2 in the front will cancel off with the 2 in the bottom. And if you notice, and you tried all of them, you will actually notice a pattern. So this has to be x cubed over 3 plus c, because when I find the derivative, I get 3x squared. The 3's in the front will cross off with the 1 in the bottom, and then we have x squared left. So all of them actually follow the same pattern. So we x to the 4 over 4 plus c. The fifth one is x to the 5 over 5 plus c. And then the last one we have is x to the 11 over 11 plus c. Now don't forget to write the constant down, the c. I can see some of you may be forgetting. So always remember that we always have to have the constant, because when we take the derivative of it, it actually becomes 0. So here are some antidifferentiation formulas that you probably know already. So when we take the antiderivative of c of f of x, the constant is still there. So it'll be constant times whatever the antiderivative is. If we take two functions or two terms, it will be the two terms added together. X to the power of n, the antiderivative is x to the power of n plus 1, all divided by n plus 1, which is what you notice in those 6 examples that we just did. The antiderivative of cos x is sine x, but notice this antiderivative of sine x is negative cos x, because when we take the derivative of cos x, it becomes negative sine. But because we want positive sine, the antiderivative has to be negative cos x. The antiderivative of secant squared x is tan x, and secant x tan x is secant x. So let's take a look at these examples here. So the first one here, we want to actually set it up so that we don't have this fraction. So I'm going to rewrite this as x to the power of negative 2. So then the antiderivative, remember the rule is we're going to add 1, and then that exponent also is placed in the denominator. So this will be x to the negative 1 divided by negative 1, and then plus c. And to write it out a little bit nicer, this whole function is, the whole fraction is negative, and the x to the negative 1 means that we're going to rewrite this is 1 over x, and then plus c. The second one, I'm going to do something similar. So instead of having it as root x, I'm going to rewrite it as an exponent to the power of half. So using, again, this formula here, we're going to add 1 to the exponent and then place that same exponent in the denominator. So when I take half plus 1, I get 3 over 2. And then I put 3 over 2 in the denominator, and then don't forget the plus c. And let's just rewrite this so we don't have the fraction like that. So we have 2x to the power of 3 over 2, all over 3, and then plus c. Okay, the last one here, I want to rewrite it so that it actually is something that I can do with. Now, we can't find the antiderivative of each part separately because there is no function that looks exactly like this. However, I can rewrite this as 1 over cos x times sine x over cos x. So I'm going to spread these out, spread the terms out. So f of x is now equal to secant x times tan x, which is actually this one over here. So the antiderivative is secant x. All right, let's take a look at a couple of other ones down on the bottom here. So here I have the first derivative and the second derivative and the third derivative. So I'm asking you to find f, which is the first derivative. So f of x means that we're going to take and find the antiderivative of this 3x to the power of 4. So we get 3x to the power of 5. So we add 1 to the exponent, so it becomes 5. And that exponent also goes in the denominator. And then plus c. Now remember, you can always do a check. So if I wanted to check, I can find that the derivative is equal to, this would be 3 times 5x to the power of 4. And I still have my 5 on the bottom, and then derivative of c is 0. So the 5's would cross off, and I get 3x to the 4, which is what I have first. All right, now this one's the second derivative, which means I need to find the first derivative. Oh, actually, before I do that, I think what I'll do is I'm going to rewrite this second derivative as x to the power of negative 3. It's always easier to write it as a term with no fraction. Okay, so now I'm going to find the first derivative, and I'm going to add 1, so be careful. So this will be negative 2 over negative 2 plus c. And then the first, not the first derivative, but just the function itself, we're going to add 1. So negative 2 plus 1 is going to be negative 1. I already have a negative 2 on the bottom, but I still need to multiply that by negative 1 in the denominator. And then plus cx, because remember it was a constant, so now we need to add an x variable, but we now need to add another constant, so we're going to call it d. So f of x is equal to, so we have negative 2 times negative 1 in the bottom, so we get 2. And then x to the negative 1 is going to move to the denominator to be positive x. And then plus cx, and then plus d.